Alright folks, today we're going to be looking at unit conversions. Now in the science world you will hear this referred to as dimensional analysis as well. Now the biggest reason it's focused on that, dimensional analysis and the word unit, is because it is a very weird looking way to do a conversion from unit to unit. But we're actually letting the units do all the work, as in we're going to look at what units are given and look at what units we need, and we're going to find a pathway to convert that units that do not directly involve the numbers right away, as in we'll have a lot written out on paper that looks like a mathematical equation long before we even get to the calculator. All right, so it is a four-step little process. We're going to actually read our question, figure out what units we're given and what we need, and then we're going to figure out a plan to convert them. Now that conversion is going to use equalities. Now equalities are something, it can be as simple as 1 foot is equal to 12 inches. We're just basically looking at a conversion or a relationship between two units that we know. The units are kind of the important thing. We're going to use those units to actually figure out our pathway to convert something from point A to point B. So as an example, if I had a question of what is the height, a person has a height of 2 meters, and if I want to know their height in inches, our given units are meters, and the desired unit is inches. Now the strategy we're going to look for here is we're going to actually look for a conversion factor that relates inches to meters. Now if we have that, if we have an equality that has units of inches and meters, we're just looking for that. But if we don't have it, like for instance, let's say we had meters and feet, if we knew that, well then we just need a second one, because we could also go feet to inches. So that's what we're looking for, that pathway. Once we have those two units, we're looking for strategy or equalities that relate those units. So that is the plan it's talking about. We're going to look for equalities, and we're going to call those conversion factors, and we'll have them from various different sources, but that is the actual strategy. Like for instance, that one that we were actually doing, the meters to millimeters probably wouldn't work out too well. Pounds to ounces wouldn't, pounds to kilograms. But if I go to our periodic table I provided you, I did give you inches to centimeters. So go back to that thing. So if we had that periodic table, I have centimeters to inches. Those aren't any useful to us anyway. But since I need meters, I would need to have my prefix conversion, which is meters to centimeters. So that is what we're looking for. We're looking for the units to tell us to set up the problem, those conversion factors. Now it seems vague that I only gave you these three, but there are other ones provided that we will use. But I gave you the main ones we need to convert any English unit to a metric unit. Obviously there are more. We can actually look up feet to miles, but theoretically we could get all of them from just these three. So that's why they're there. All right, so what do we do once we have that? Those equalities are going to give us that unit conversion. So they can be anything. Got that 1 inch equals 2.54 centimeters, which is the same as on that previous slide. It might even be somehow related to like a food label. So most food labels in America, they will list the net weight in ounces or potentially fluid ounces, and they'll also tell you typically that volume in the metric and the milliliters. All three of these actually, or these two actually have quarts or pints. But you could use these as conversions. So this is actually kind of saying that 16 ounces is equal to 453 grams. This one here is telling you 16.9 fluid ounces is equal to 500 milliliters. Now, there's going to be some limitations to this. This is probably not the best route to use, but those theoretically are equalities. Now, the biggest reason they're listed both ways in America is because of the weird restrictions we have on things. Even the fluid ounce and ounce don't necessarily mean the same thing anymore. So the metric is a kind of more concrete, and we're seeing that to be a little bit more of the norm on most of our stuff in the United States even now. All right, so those equalities are what we're going to actually refer to as conversion factors. Now where it changes, the equality is just that 1 equals 2.54, but remember I said we're going to shred this up to cancel out units? Like that problem we had 2 meters was the person, and we want to know their height in, I don't even remember what the question was now, height in inches. So we wanted to convert, that strategy was to convert meters to centimeters. Well, I'm turning that equality into a fraction, and I'm setting it up in such a way that the units change. Even this next one, I'm going to have centimeters to inches. Now what I just did was elaborate on these 2 steps we just did. They were equalities, and I turned them into fractions. And I set them up so the units cancel as we go through. Now to turn this into conversion factors, we're putting those in there. So 1 inch equals 2.54 centimeters, and 1 meter is 100 centimeters. And that gives me a mathematical equation that will essentially turn my meters into inches. And it's just like any old fraction you could use. So I know this is a fancy TI, and I can actually do it so it looks like this with the fractions, but I don't necessarily need to. This is just 2 times 100, because I'm going to ignore that 1, and then divide by 2.54. And I get that 2 meters is roughly 79 inches. Now it did give 2.0 meters, so I need 2 significant figures. So the proper answer for that is just 79 inches. Now that's the gist of dimensional analysis. We got our given units, we got our desired units, and we're going to develop conversion factors from equalities to get a pathway to convert those. Now, for the rest of this lecture note, we're basically going to do some of these as practice, because we got a bunch of different ways you see these. Sometimes those conversion factors are going to be based as percents. So a very common thing we see on food thing is they'll just say 30% of whatever something is in there. Now, by definition, unless it says something after that, it needs to be a 30% by mass. So even on like a soda or a liquid, if it doesn't say anything different, it's the mass of whatever they're saying compared to the mass of the solution. So if it says 30% by mass, that means there's, for every 30 grams of fat, there's 100 grams of food. That's kind of what a percent it means. So we can turn that into conversion factors to convert grams of food to fat. So conversion factors can be a lot of different things. We can see them in parts per million and parts per billion. Now, these are weird. I don't necessarily typically write it out like this. I typically do more like this. So if I wanted to talk about the 15 parts per million cadmium, what kind of we're doing is the grams of cadmium over the grams of solution, and it is just a mass to mass ratio, just like the percent, but instead of multiplying by 100, we're multiplying this by 1 billion to get that ppm. Now think of ppm, and oh, I did multiply by 1 million. It says ppm, that should be multiplied by 1 million, not 1 billion. So that should be 10 to the 6th. Now, this is typically done when we're talking about really, really, really small numbers. Because if I had actually released these 2 numbers with the exact same units, a kilogram compared to a milligram, we're talking about this in grams, that's 1,000 grams, and this in grams is 0.015 grams. Now, if you compared those and looked at them, it's like there is practically nothing in the of that. Because, if I take the 0.015 and divide it by 1,000 to get the actual ratio, this is just a ridiculously small number. 1.5, but technically has 4 zeros in front of it. If you release that and told you that's how much cadmium was in somebody's food, they're not terribly worried about it. But because of how toxic this is, to draw attention to it, it's a big number. We came up with that conversion factor to ppm. So if I multiply this by 1 million, I get it into the proper significance here of 15. And we see this on a few things. Lead in the water, cadmium in the water. These are the type of things that get tested for all the time to make sure we don't have any dangerous amounts in there. But these are technically conversion factors, and we all see it. All right. Other weird ones that pop up, you're going to get more familiar with this in later health classes, but LD50 is typically not one that's actually a go-to all the time because it really is a lethal dose. As in, if you have this much, 50% of the time, the people are going to die. Right? You would want to be nowhere near that number, and gosh, if it has an LD50 that's even remotely reasonable, that's probably not something we do too much of anyway. But it is something that's tested. So what that translates to is everything that's ever been tested, even aspirin. We know what its LD50 is, but it's going to be some ridiculously huge number, I would imagine, which is why not many people die from taking aspirin. But it is a conversion factor because it's going to be related to grams over kilograms. And it really depends on what's going on. So some LD50s, depending on how toxic it is, might be micrograms to kilograms, parts per billion. And some of the more dangerous stuff that we know is dangerous might be grams to grams, right? Because, it can be that way. So the LD50 doesn't have a definite unit, but it is something that is technically a conversion factor because it's milligrams of whatever you're dealing with compared to, or whatever grams it is to what you're comparing to whatever gram unit is the stuff you have in there. All right. So when we actually do this, these calculations, and I just did this one, and I actually told you two significant figures because that was 2.0 as it was given. Now, what I was looking at was a significant figure problem. So if we back up and think about it, when we were talking about significant figures before, we said this 2.0, we counted that 0 because there was a decimal there, so this was two significant figures. When we do multiplication, we look at the smallest number or the number with the least amount of significant figures, which is that 2.0, and we want our answer to also have two significant figures. Now, these guys are kind of definitions exact, so we never round on those. I mean, that 1 inch is 2.54. We don't worry that that's just one significant figure. These are definitions. So the rounding was done because of that too. And that's what it's talking about. On multiplication and division, we actually do just find the number of the fewest number of significant figures, and we'll round to that. So if I were to do this 110.5 times 0.048, I do get 5.304. But since that 0.048 only has two significant figures, I'll have to round the answer to just two significant figures. Now, for the most part, this one makes sense. And when we do practice, we'll see this a lot because you really do just look for the fewest, you ignore any exact numbers, and then you round it based on whichever one's the fewest. The one that's a bit more challenging is addition and subtraction, because the number significant figures in the question, the values given, don't necessarily guarantee the same number of units in the final answer. Now, why that is, so if I looked at 25.2 and 1.34 and added them, that's what my calculator will give me. But remember that weird idea of the uncertain number? Because that is that last digit, that 2 there is uncertain, and on this one the 4 is uncertain. But when they added together, that uncertainty in the 2 would have translated to uncertainty there. So when we round on adding and subtracting, we're looking at the numbers, finding out which one has the least significant digit, and we're going to round to that on all of our answers. All right, now we're going to practice this a lot, and I have the calculator up here because a horrible thing is your calculator will always round based on what's simple in the calculator. It will never rely on significant figures. And we might even have to add digits. So we're going to practice this a lot just so we make sure we get this right. And when it comes to rounding, we're going to follow the same rules that we've learned all of our life. 4 or less, we round down. 5 or greater, we round up. So no changes there. All right. But I do want to remember this and have this and stress it again. If my calculator gives me 4 on the nose, yet I know I have more significance, or I know I need more significant figures, I can always add zeros. So we'll have to do that some, and obviously the calculator won't necessarily get that. And we're going to see some examples on that. All right, so summary of this, and now the rest of this is just a bunch of times to practice this stuff, various different little calculations to work through. Now, a lot of the time, we're going to have ones you probably could do in your head without too much difficulty, but I'm going to write it all out just to go over the steps. All right, so we are looking at a given unit of hours and turning to minutes. So our strategy is just that. Fortunately, this can be a single conversion because I think everybody knows how many minutes are in an hour. So I'm going to write down the 2.5 hours, and then I'm going to have just a single conversion factor that converts hours into minutes. And I have hours on the bottom, so those units cancel out. And then I just add in my number. 1 hour is 60 minutes. Then I just need to take 2.5, multiply it by 60 to get my answer. Well, remember, can't rely on the calculator to give me significant figures, so I'm looking at this. That 2.5 has 2 significant figures. This is a definition, so I don't worry about that. Therefore, my answer should have 2 significant figures. So I'm going to write that 150 down without a decimal, so we get to ignore that 0, and then I just put the units there. All right, slightly more complex. Actually, this is not. This is easy. 2.44 meters, and I want to convert it to centimeters. I have meters, and I can definitely do that in a single conversion because that's kind of a unit definition. All right, so 2.44 meters, and I'm going to convert meters to centimeters, and now I just need to remember my prefix. 1 meter is 100 centimeters. And gosh, if you feel comfortable just moving the decimal, you definitely can. But 2.44 times 100, 244. Piece of cake. All right, have a slightly bigger one because I doubt too many people know how many minutes in a day. And you don't need to know that. We don't need to have that memorized because we can convert days into hours and then hours into minutes. And I think everybody knows how many hours in a day and how many minutes are in an hour. And then we're going to let the calculator do all the rest. So I'll have to have a conversion from days to hours, so the days cancel out, and then a conversion that goes from hours to minutes, so the hours cancel out. And there's 24 hours in one day and 60 minutes in 1 hour. So 1.4, oops, I dropped my 1. 1.4 times 24 times 60 is 2016. I have 2 significant figures because that 1.4. So I would have a problem with this one because the answer is like 2000 because I'm rounding off at that tenths. I need to show that number significant. So this is when I have to do it in significant figures. That's 1, 2, 3, and then I can put minute. But about the only reason I need that significant in scientific notation is to show those 2 significant figures. All right, let's go a little bit more complex because I didn't give you enough to do this when on here. I didn't give you any units. So I gave you just liters, and I want to know how many gallons that is. All right, so I doubt anybody knows how many liters are in a gallon or vice versa, but I did on the periodic table give you liters to quarts. Now here's an interesting thing. Quarts to gallons, that's a very American thing. I typically give that to you on the test because I don't expect everybody to know it because it's a weird English to English conversion. But you know, this is probably one everybody knows because quart, the quart part, that's got to be 4, right? All right, so I got 4.65 liters. Now this conversion is known more precisely than I have on the back of that periodic table, but I gave you a ridiculous amount of digits here. Oh gosh. 0.946353 liters. Is 1 quart. 946,353 liters, 1 quart. Make sure I got that number. 946,353. Yes. And then quarts to gallons. 4 quarts to 1 gallon. 4.65 Oop, I dropped the decimal. And then divide by 4. And I get that that is about a gallon with 3 significant figures, so this should be 1.23 gallons. Alright, another one of these fun things. I got a ski pole that's 3 feet in length, and I want to know how tall that is in millimeters. Right. Another one I probably don't know, and since I doubt many people know how many millimeters are in a foot, I chose this one because I did this horrible thing to you. On the conversion, I gave you inches to centimeters. Didn't give you enough. But I do believe that everybody could convert feet into inches. And then from that periodic table, you could go from inches to centimeters. And then once you had centimeters, you could go to millimeters. All right. So, 3 feet. And feet to inches. So the feet go away. Inches to centimeters. So the inches go away, and centimeters to millimeters. So the centimeters go away. All right, putting numbers in here. 1 foot, 12 inches. 1 inch is 2.54 centimeters. That's on that slide. This is a weird one. Let's say you didn't remember how many millimeters were in a centimeter, but you remembered that there was 1,000 millimeters in a meter and 100 in a meter. So isn't this weird? 1,000 millimeters in a meter, 100 centimeters in a meter, those can be used as a conversion factor. There's 1,000 millimeters is equivalent to 100 centimeters. It's just kind of weird, but it does work. You can do stuff like that. All right, so 3 times 12 times 2.54 times 1,000 divided by 100. Just multiply by everything that's on top of a fraction, divide by anything that's on the bottom, and I'm ignoring the ones because divide by 1 doesn't do anything. And I get that that's 914 millimeters, but I want 2 significant figures, so 910 millimeters without a decimal. All right, got another fun one, but this has multiple units in it. We have 65 meters per minute, and we want to know how long it's going to take you to walk a distance of 7,500 feet. Ooh. All right, so I'm going to start with that unit I'm given, feet, and I want to turn that into minutes. All right, the last one tells us how to convert those. We're going to go from meters to minutes with that pace. So my trick is to go from feet to meters then. And I'm going to do that long way I did before. So inches, and then inches to centimeters, and then centimeters to meters. Because that's that equation that's given on the periodic table. That's a definition we know, and this is a definition of prefixes. And we're using this weird thing, 65 meters per minute, as a conversion factor, because that is just an equality. All right, so 7,500 feet. We're going to go from feet to inches, inches to centimeters, centimeters to meters, and then one that doesn't make a lot of sense, but meters to minutes. It's unique to this problem. All right, so how many feet in an inch? Well, there's 1 foot is 12 inches. 1 inches is 2.54 centimeters. There's 100 centimeters and a meter. And our last weird one, 65 meters covered in 1 minute. All right, so 7,500, a little over a mile, times 12, times 2.54, divided by 100, and then divided by 65. 35 minutes. Now, this doesn't have a decimal, so it's only two significant figures. But unlike all the previous ones we did, this is not a defined motion. That's the actual rate. So that's 65, we'd have to look at that. That's only two significant figures as well. So our answer is two significant figures. 35 minutes. And even though that seems slow to walk a little over a mile, I got to tell you, if you were able to maintain that pace that entire time, more power to you. Because that's most people speed up and slow down. So if you maintain that rate at over a mile, yeah, you should be happy with that. That's you know, the Olympics, they have the people who professionally walk. If you could maintain a pace as a walker, who cares? You're still getting that distance done. All right. I have this wonderful one that uses one of those conversions that's just given as a percent. All right. So I have grams, and I want to go to pounds. But I'm going to write a little bit more. I have grams of candy. I'm going to specify what it is. And I want pounds of sugar. All right. What I need to do is convert the candy part out into just the sugar. And I can do that with this conversion. This conversion can actually turn grams of candy into grams of sugar. Because we're getting less. There's a lot more candy than there is sugar without converting into grams. But then I have to go from grams to pound. Now, there's probably somebody taking this class that knows the general conversion that we use in the medical field, which is this. It's the 2.20462. Most of them are going to remember 2.2 because if you're dealing with a human, having two significant figures, and technically you'd have three if you remember 2.20, is a lot. But we're going to use that full thing, and that converts pounds into kilograms. So I need to convert this to kilograms, and then I'll be able to use that number to convert it into pounds. All right, this is going to be a fun one. 120 grams. Now use this as a conversion. Now that's 25 to 100, and this is grams of sugar to grams of everything, in this case the candy. And that's what's going to go over here. So this was candy. I'll just do a C there. So I'm going to put the 100 grams of candy on the bottom. So those units cancel out to 25 grams of sugar. And I'll just do S. And then I'm going to convert that to kilograms. And then I'm going to convert kilograms into pounds. 1 kilogram is 1,000 grams. And I want to get all those numbers. So 2.20462. pounds for every 1 kilogram. Now this really isn't much sugar, right? 120 grams isn't a lot. So we're not expecting a huge amount of pounds, but let's see what we get. 120 times 25 divided by 100 divided by 1,000, and then times 2.20462. And I get this big, huge number. Not many pounds. All right, but that wasn't much sugar, really. Not much candy. All right, but this 120, two significant figures. This is just two significant figures. This is kind of got some significance to it, but I gave you a lot of extra digits, so you shouldn't never have to worry about rounding there. But so I should get two significant figures on this. So my answer is 0.066 pounds. All right. LD50 for aspirin is 1100 ppm. How many grams of aspirin would it be lethal if 50% of the persons with a body mass of 85 kilograms? All right. I'm going to expand this as a conversion factor. Now, our plenty of places show it with change in the unit to micrograms and whatnot. I'm going to do it more like an actual mass. So 1100 is like saying 1100 grams of aspirin compared to 100 grams of a person. Actually, no, I got something wrong there. Oh, no, I'm fine. 100 grams of a person, and then we're multiplying this by, since this is a million, 10 to the sixth. And I'm just going to do person. So this is going to be my conversion factor, right? No, I got this wrong. This is equal to the 110. Yes, I don't know this. All right, so I'm going to manipulate this so I have the grams. I'm going to figure out what the grams of aspirin would need to be. So what I'm going to do is take that 1100, sorry, divide by the million to move it over there. Move this over by multiplying by 100. All right, so this is telling me that this conversion factor to get that 1100 is 0.11 grams of aspirin to every 100 grams of person times the 10 to the sixth. That is my conversion factor. Now, I don't have it necessarily set up right. I might end up flipping this, but I'm going to show you how we're going to do this. So what we're going to do is we're going to take the kilograms of person and turn it into grams of aspirin using this thing as a conversion factor. So I have the 85 kilograms. All right, it's going to work out just fine because I do want to cancel out the person, so I'm going to end up using it just like it's written. But very first thing I need to do, because this was grams, is to convert this into grams. So I have kilograms to grams. 1 kilogram is 1,000 grams. And then this thing is going to go into a conversion factor all by itself. I'm just going to do something weird with that 10 to the sixth. So it's multiplied that to get to that ppm. I'm going to move it up here with the aspirin. So times 10 to the sixth. And then on the bottom is just everything else. 100 grams person. All right, so I have the kilograms canceling and the grams and the person canceling. All right, 1100 ppm. Let's see how much aspirin this actually is. 85 times 1,000, then times 0.11, times the million, and then divide by the 100 gram person ratio. Huge number. All right, moving on to another one. Density is another one that can be turned into a conversion factor. I'm going to explain what density is, though, first of all. So density is just basically a ratio of an object's mass to its volume. Now, most substances, it has a fixed density. It might vary with temperature. For instance, water, and I can do this very rough, is pretty much always 1 gram per milliliter. Now, that sometimes written as 1 gram per cubic centimeter, but it is kind of how we used to define these. A milliliter is roughly a cubic centimeter because it is with water. All right, the truth of the matter is water is really only 1 gram per milliliter, right around 4 degrees Celsius. Above that it goes down a little, below that it goes down a little. So then there's big huge tables you can look up, but it does change, but it's almost always going to round to 1, because when it's not 1, you can kind of guarantee it's 0.99 something. The first 2 digits are going to be a 9, but it is done that way. But, you know, it's kind of neat. On solids and liquids, you almost always see grams per milliliter or grams per centimeter, and they do. We do allow them to interchange. They swap. But generally speaking, we try to do grams per milliliter for all liquids and grams per cubic centimeter for all solids. And we try to be pretty consistent about that. But you see those two exchange because we've done, for ages, defined these as the same thing. All right, now for a gas, though, because gases are much, much less dense, we typically see units of grams per liter. because they occupy such a bigger run. And it's basically a way to get the units to move over. All right, but you see grams per milliliter, grams per cubic centimeter, or grams per liter. These are equalities, and we can use them in conversion factors. And that's why there's tables galore of these. Now, most of the time, if you ever see a table of densities, they're going to list the temperature at which they're taking. And in a lot of cases, they'll actually put more zeros on this, like 25.0, because they do go out of their way to get those temperatures pretty routine and solid. Now, what's interesting, there are plenty of things on here that vary. Wood, for instance, even if it's maple, there's going to be reasons why that density might vary over time, or even how dry it is. But most other things, especially some of our elements, those are kind of set in stone. They're right. And even urine, about the only time it varies based on very good reasons. So it's something that the density is measured just to actually see if there's issues. Same with blood plasma and blood in general. The density should be fixed, but if it's off, there's medical reasons why it could be. And there's definitely medical reasons why it gets checked, obviously. All right, so let's actually apply one of these. I got osmonium, very dense metal, has a density, I want to know what is its density in grams per centimeters. If it takes 50 grams, has a volume of 2.22 centimeters. Well, fortunately, the units tell us how to set this up. 50.0 grams per 2.22 centimeters would leave us with grams over cubic centimeters. So that's all we do. 50 divided by 2.22. Huge density here. 22.5 grams per cubic centimeter. I don't even think that was on my chart, was it? Now, I have some of the metals, but I didn't have that one. Look how dense gold is. But, you know, some of those metals make sense. I mean, what's going to happen to a piece of gold if you put it in water? It's going to sink. I mean, everything that's more than one is going to sink. All right. The volume is an interesting thing. So in the lab, we can get the volume by displacement of water. So a very common way to do this, we actually get a very good graduated cylinder, so what this thing is called. Fill it with some water, enough water that you can submerge an object into there, and then you just drop the object in there. If it goes from 25.0 to 33.0, and there's no other bubbles on there, and that thing is completely submerged, you know it's what displaced the water. There's still just 25 milliliters of water in there, so everything else must be the object. So I just do a simple problem, math problem. 33.0 minus 25 gives me 8. And this is a subtraction problem, so we have to do that with that significant figures. We're uncertain there, we're uncertain there with the tenths place, so we know this is 8.0 milliliters, and there's a little bit of uncertainty on that 0. So the volume of that metal is 8.0 centimeters, or 8.0 milliliters. So I just take the 48 grams that's listed there, divide it by 8, and I get that whatever this is has a density of roughly 6.0, because of two significant figures there, grams per cubic centimeter. All right, kind of already just talked about this, things that sink and fall. It is based on the density of the liquid they're in. So if the liquid is water with a density of 1, the cork and ice are going to float on top of that, and the aluminum and lead, which are heavier, are going to sink on it. Now, we do see some weird things that show how things can separate out. Now, syrup, for instance, and vegetable oil and water will do this. But sometimes, so especially that Karo syrup, that is basically sugar water. If you have that just with water and you shake it, shake it, shake it, you can generally get those to mix and stay separate. Or stay as a unique thing, because water will dissolve into that. But if I do it like this, where I have these things set up and I do it nice and slow, I can typically keep that layer separated. Now, technically speaking, my heaviest density would be at the bottom, so that's got to be that Karo. The next one's got to be the water, because it's got slightly less, and then the oil sits on top of it. And the oil is kind of even like gasoline. That's the biggest reason they can't use water on gas station fires, because the gas just sits on top of it and the water doesn't get a chance to smother it. So they actually have foam that comes out of those things that just smothers out the fire instead. All right. All right. Here's one. I gave you the density, and I know what I want to. So it's octane component of gas has a density of 0.702 grams per milliliter, and I want to know what is its mass in kilograms of 875 milliliters of octane. All right. So we're going to start with those milliliters. We're going to use the density to help us convert into grams. And once we have grams, we're going to use our definitions to turn that into kilograms, which is what we want as our final units. So I have 875 milliliters. Density will convert from milliliters to grams, and it's 0.702 grams for every milliliter. And then grams into kilograms. 1 kilogram is 1,000 grams. 875 times 0.702 divided by 1,000. 0.614, and I'd have 3 significant figures here and 3 there. So my answer has 3 significant figures. 0.614, and this would be kilograms. All right, we're not going to bother with that one. This last weird one is I didn't give you everything necessarily need. I'm just wanting to know what will displace the most water. So which of these has the largest volume? Now to figure that out, we are just going to take the mass, and all 3 of these, it's in grams, and we're going to manipulate the density as a conversion factor. So the grams are in the bottom, milliliters on top. So without putting the numbers on any of these, the 25 goes there. Oops, I dropped my 2. 25. And then this would turn into 2.7 over, and the 1 is on the top. So I'm dividing that by 2.7. So that's going to occupy about 9.2 milliliters. No, 9.3 because I'm around. The next one is 45. 45 divided by 19.3. 2.3. And then 75 divided by 11.3. One that displaces the most volume? That one. Alright, now the reason I wrote it out like that and left this vague, I do want you to focus on the units, because a common mistake is I would have got people taking the 25 and just multiplying it by 2.7. So at least write out the units so you see what's going on, so you can set up that conversion factor and not get caught with a simple mistake, because that would have been an easy calculation that wouldn't have been obvious. And if you get a question, if you send me a question and I actually just write back a very vague statement of check the units, I'm probably pointing out that you've missed a unit conversion, and that is what you're doing. You just need to go back and then double check that and look for simple mistakes like you don't have the units quite canceled out right. All right. Have any questions? Send me email. If you see anything you want me to go over anywhere, send me an email. Come see me even.